Hello, good morning all. In this lecture, we are going to start with the wave mechanics part of the quantum mechanics. Okay, a few of the things we have left right now for the first, you can say, uh, first exposition. I want to directly start from the wave function, assuming that you know the development till wave function. If you don't know, don't worry about it. We'll do it in modern physics. But overall, we'll start directly from having an understanding that there is some construct called as wave function. Okay, and we'll do a little bit of quantum mechanics on the wave mechanics side. In parallel, we are already running linear algebra, and sooner we are going to reach to a point where we are going to start with the matrix mechanics. Okay, as propounded by Werner Heisenberg. So, without wasting time, let us start. See, let us take a particle of mass m, and let's say it is constrained to move in the direction, let's say x-axis, subject to a force which is a time dependent and let's say x dependent force. Now we know that the velocity of this particular particle can be written as m dx by dt. Similarly, if someone asks me what would be the momentum, I will write it as m times v. If somebody says what would be the kinetic energy, it would be half mv square. Okay, and in fact we can apply, if it's a conservative system, if it's a conservative system, then we can apply, if it is a conservative system, then we can apply energy conservation and things like that. Okay, so overall understand that in the framework of Newtonian mechanics allows us to determine the position of the particle precisely as a function of time. Gosh, this is not visible. As a function of time, and just give me a minute, I think. Okay, so as a function of time. So what is the governing law for the quantum mechanics? Uh, this is what is a query. This is what is a query. Okay, so just give me a minute as go along with this. I hope now it is visible. Okay, so let me see if that's working here. Okay, just give me a minute. Okay, let me see if it's visible now. Okay, so as I told that initially that we are starting with the wave mechanics part of the of the quantum mechanics. I have told that I'm going to assume that you know already the formulation of the wave function. Okay, even if you don't know, don't worry about it. We'll see all these things a little bit later also. But let us start at first because we are lagging a little bit behind in our course. Understand that quantum mechanics has been divided into two parts. One is wave mechanics, which was propounded by Erwin Schrödinger, and another part which is more mathematically motivated and is a beautiful part of quantum mechanics, is it was propounded by Werner Heisenberg, and it is called as a matrix mechanics, and for which you need a sound knowledge of algebra, that is linear algebra, and which is something that we are doing right now in parallel. Okay, so, wave mechanics, as propounded by Erwin Schrödinger, uh, this is an important part here. Here we will actually start with directly assuming that we know the wave function. I was telling initially that let's say if you have a mass m and let's say it is constrained to move on the x-axis, I know that the force equation, let's say whatever force it is being subjected to, can be equated to mx double dot, and it allows me to extract x as a function of time. it allows me to extract x as a function of time. Okay, so given some initial conditions, I'll be able to find x as a function of time. And if I know x, then I know what would be v as a function of time. And if I know v, I will know what is p as a function of time, because it is nothing but mass times velocity and all those things. So there is a sense of determinism here. There's a sense of determinism here. Now, the same all for for let's say in quantum mechanics, in classical mechanics, we have certain motional laws, right? We have certain motional laws. Let's say this is one of the Newtonian law, which says that whatever force you're going to apply, it is equals to mass time acceleration in that direction. Okay, so the same question arises: what would be a law which the quantum mechanical objects are going to abide? So one of those laws is time independent Schrodinger equation. Okay, so instead particle is represented by a wave packet, or you can say mathematically by a wave function here. Okay, so I'll write it here. So in quantum mechanics, especially in wave mechanics right now, then we'll see Ket and Brown rotation. All those things we'll see in the uh, in you can say in our matrix mechanics side. Okay, so in quantum mechanics, the wave function abides equation. Let's say right now I'm concentrating on time independent equation. So abides something called as Schrodinger equation. Okay, something called as, just give me a minute. Okay, something called as Schrodinger equation. Okay, and right now we are actually concentrating on time independent Schrodinger equation, and a few of the things related to it. A few of the things related to it. Okay, a few of the things related to it. So let us start with that. Okay, so just give me a minute as I start for you. Just give me a minute. What's happening here? Okay, just give me a minute. Actually, there is a problem with the pen. Okay, so how it is given? Just give me a minute. Actually, this is how it is. Okay. Okay, so it is given by this. So I'll write iota h ket del psi upon del t is equals to minus of h ket square upon twice m, and then you have del square psi upon del x square plus v psi. Depending upon different potentials, we are going to extract different wave functions. We are going to extract energy eigenvalues, and this would be our motivation for this particular section. This will be our main motivation for this particular section. That is, what we are going to do, we are going to use different potentials, let's say different one-dimensional potential, two-dimensional potentials, and we are going to see how things, how this wave function evolves, how, what is the expression of the energy eigenvalues and such things. Okay, and the same thing we are going to see even in our course in matrix mechanics, but the representation would differ. The representation would differ. Okay, so this is part one. Now, um, okay, uh, we have done a lot amount of things, like we have already done what you can say. We have already done something like Fourier transform and all those things. I would recommend that you just see all those things, because that they are very important when it comes to formulation of wave function. Okay, so I'll come to all those things. Okay, but first understand that what does this psi represent. I'm going to write what does this psi represent. So you can say that a state, or you can say a quantum mechanical state is represented by a wave function, represented by a wave function. Okay, and all these things are related to wave particle duality. That is something a part of modern physics that we're going to take later on. But understand that a particle can be represented as a wave packet, and the equation and that conceptualization leads us to wave function. Okay, okay, and this particular wave function represent a quantum mechanical state. Okay, it represents a quantum mechanical state. Okay, so whatever information we can get about a system, let's say a quantum mechanical system, is contained in this psi. So I'll write it here. So this particular psi contains the all the maximum information that we can extract, that we can extract for a quantum mechanical system. Okay, so in three dimension, I'm going to write it as this way. So in three dimension, if someone says what is psi, psi would be probably function of x, comma y, comma z, and in fact, it can be function of t as well. But right now, since we are doing time independent, we will not consider it as a function of time. Right now, we are going to consider it as a function of x, y, and z only. In general, it can be function of both time and you can say space. So I can write this way. Okay. um, Later on we'll see that a useful way of this is sometimes called as the coordinate representation. Okay, later on we'll see that there are few problems, quantum mechanical problems, where it is advisable, or you can say it is better uh, to see a wave function as a function of momenta or probably wave numbers rather than coordinates. Okay, so there we would use something called as Fourier transform in order to change our wave function from coordinate space to the momentum space. So just I'm writing right now, don't worry about all these things, but just a little bit of note I'm writing here. So in a few problems, it is better to visualize the state of the quantum system in momentum space. Okay, in momentum space. We'll come to all these things later on, but just remember this thing. And what we are going to use here, so I'll write it here. So let's say if we are discussing, I'm writing, let's say we are discussing a system with 1 degree of freedom, let's say with 1 degree of freedom, which would imply what? Which would imply, let us say that I am discussing psi as a function of x only. Okay, so if that's the case, how to change your wave function from coordinate space to momentum space? This is how you do it, by using the Fourier transform. So I'll use by using. So if you have not taken lectures on Fourier transform, I'll write the formula here. Don't worry. So if I want to write the Fourier transform of, let's say, psi x, so psi x would become this particular thing is called as a Fourier transform, and I'll write it as dx e की power minus iota kx, and then you have psi x. So if I want to take the Fourier transform of psi x, this is equal to this. This is the kernel of Fourier transform. Okay, and you can say that psi x can also be as well written in terms of an inverse Fourier transform, and usually some constant 1 upon 2 pi is also written. Forget about this, even 1 upon 2 pi can also be written here. You can forget about this also, don't worry about this. uh, this can be written as dk e की power iota kx, and then you have this psi k. So if I follow this particular thing as I have given you, that that if I want to change my wave function from coordinate space to momentum space, I need to take a Fourier transform. I need to take a Fourier transform. So what I'll use, I'll say that my P is related to this K by this. So instead of K, I can write psi P upon h ket. This is something that I'm not deriving right now. We'll see all these things later on because I've just started. So I'm just writing it here. K bar iota minus px upon h ket. Okay, so this is how you can convert your wave function from coordinate space to momentum space, and likewise you can write your wave function in coordinate space using wave function in the momentum space. I mean, this is very necessary, let's say when we are doing collisions, okay, when we are doing scattering problems, okay, so there it happens so that you have the information in terms of momentum profiles. So that is why at times this becomes very necessary, that instead of x, you'll have this momentum specified. Let's say you are doing some scattering problem, and there you have momentum profiles. Okay, so you need to define wave function in the momentum space, and which would require you to take a Fourier transform. Is that clear? Okay, because see, I can write it as a note also here. Okay, so since you know that a classical system holds a sense of determinism, holds a sense of determinism in terms of fate, in terms of fate of it. Let's say I'm saying that I have given some initial velocity to my system, and let's say it is under the influence of gravity, so obviously it is going to go for a parabolic trajectory. Okay, if I, let's say, give a little bit more force to it, probably let's say escape velocity, then it is going to go for an electrical trajectory around the earth. Okay, if I give it a force which is equal to the escape, if I give it a velocity which is equivalent to the escape velocity, it is going to escape the earth. If I'm going to give it a velocity which is, let's say, orbital velocity initially, then it is going to go for an elliptical trajectory. So the fate of the system is quite determined when it comes to the classical systems. When it comes to the classical system, all you need to specify me is x. All you need to specify is let's say x and probably v. See, whatever I've told. Let's say if I'm just dropping it. Let's say if I'm just saying that velocity initially is 0, so it is going to execute a free fall, isn't it? If I give it a slightly some velocity in this direction, it is going to make a parabolic trajectory. If I give it a velocity, let's say orbital velocity, it is going to orbit around the Earth, which is an elliptical trajectory. And let's say if I give it an escape velocity, it is going to escape in a hyperbolic trajectory. It's never going to come back. The point here I'm making is that if you specify me x and v, I can determine the fate of the particle at any instant of time. This is what we mean when we say that the classical system holds a sense of determinism. Okay, so you just specify me x and v, and in terms of when I say v, I can say x and momenta, and you are done. This is why we say that the classical mechanics is well represented in phase space, is well represented in phase space. Now in quantum mechanics, what happens is, in quantum mechanics what happens is psi in general cannot depend upon x and p. Like psi cannot, I'll write here, psi cannot depend upon both x and p simultaneously. Why? Because of the some very inherent uncertainty around it, which is known as Heisenberg uncertainty. This we are going to see later on, but understand that x cannot simultaneously depend upon x and p. Okay, because somebody may say that if you know, let's say if I know x, then uh, if I know x and if I differentiate it, I know that I can relate it to p. But it's not that easy in quantum mechanics. Okay, because psi in quantum mechanics, momenta and this particular coordinate, that is x and p, they cannot be simultaneously and accurately be measured. This is something that we are going to see later on. But understand, this is something probably if you've done your BSc section, you know that this particular computation is not equal to zero, rather it is equal to iota h ket. Okay, so I know that they cannot be simultaneously and accurately be measured. That is, they are governed by some uncertainty principle, which is called as the Heisenberg principle of uncertainty, and therefore things are not easy inside, and therefore we take a resort of some different space, and which is called as a Hilbert space. So we'll say that the wave mechanics in quantum wave mechanics, or probably quantum mechanics, the wave function resides in Hilbert space, and this is something that we're going to again see later on. I mean, is that clear till now, or am I making some sense, or am I not making any sense? Because this is an introductory lecture, and I usually get confused as to what should I speak on introduction and what should I refrain from doing. So all these things right now I'm stating, you can say as like a postulate I'm stating, and later on you're going to see as we progress in our course that we are going to have some sense of understanding. Is that clear? Please let me know. If it's not clear, then I will have to repeat it. Uh, Okay. Now, having said all these things, let us start with directly with the time-independent Schrodinger equation, as I stated. Now, the question arises: what does physical representation of psi is? So, psi I have already stated. It represents nothing but it represents the state of the quantum mechanical system. When we are going to see all these things in when we are going to see all these things in what you can say matrix mechanics, we are going to write these things in ket and Brown notation, and we are going to represent it in this form. Okay, so right now, as I'm doing wave mechanics, I'm going to use this only. This represents the state of the quantum mechanical system. Now, according to Born, there was another scientist Born who actually you can say explain what is the physical phenomena, not of this psi but of psi mod whole square. Okay, psi mod whole square. Okay, psi mod whole square. And what does it represent? So I'll write that the absolute square value of this wave function represents what? It represents the probability density. It represents what? It represents the probability density. It represents the probability density of what? Of finding particle, Let's say I give psi and I write psi as a function of x and t. And if I'm saying what is psi mod whole square, it is nothing but it is equals to psi star x comma t, and then you have again psi x comma t. Okay, this is equivalent to taking the conjugate. Psi star means taking the conjugate. In general, remember the psi is a complex valued function in general. Okay, psi is complex valued. Now you see, if I take psi star psi, it is going to be some real quantity, and this real quantity represents, which is absolute square value wave function. It represents the probability density of finding a particle at time t and point x and point x. Is that clear? Okay, so this is one thing. And let's say if I use the same thing in terms of momentum space, I can write that, or you can say, let's say this is one thing. And if I write this way, so this is probability density. If I want to write the probability of finding the particle, what I'm going to do, I'm going to write this way. So density means what? Probability divided by something. Let's say length, probably volume, probably that way. But if I multiply it with dx, it represents what? It represents the probability of finding the particle in the you can say x to x plus dx, in the spread x to x plus dx. Okay, similarly if I want to write these things for let's say uh, momentum space, what I'm going to write it as, so psi p comma t mod whole square, and 1 upon 2 pi comes because of the Fourier transform. This particular dp, even if you don't write it, it would be no issues, but I'm just writing it for the sake of explaining that I have taken a Fourier transform. So psi p comma t mod whole square dp represent what? It would represent so same thing, the probability of finding the particle, probability of finding the particle, probability of finding the particle uh, in the you can say momentum interval of p to p plus dp. Okay, now arises another question. Okay, so now arises another question of measurements, of measurements. Okay, so as I told you that in quantum mechanics, I'll write it here. There is a lack of determinism. There is a lack of determinism, and the outcome of a measurement is probability driven. Is probability driven. Okay, so let us say, let me explain you a little bit about all these things. So so in general, uh, you can say that if I make a certain measurement, if I make a certain measurement, um, then your wave function collapses to a certain state. A wave function collapses to a certain state with a probability, with a probability. So you can say that when it comes to quantum mechanics, what happens is, one one of the things that becomes very prominent is taking the average average when it comes to moment when it comes to explaining, you can say, measurement theory. So what I want to explain is, I'll write it here so that it will be easy for you. Okay, just give me a minute. I'll write it for you. So okay, so I'll say it here. I'll write it here, a little bit of it, so that you'll be able to understand. Okay, all these things we are going to see in postulates. Okay, we are going to see all these things in postulate, but right now, because I have started directly the wave mechanics, so measurement in quantum mechanics. So you understand, because uh, the microscopic objects, you can say the microscopic particles, are governed by something called as wave particle duality. They are governed by wave particle duality. So prior to measurement, you can say that particle does not have a specific position. Particle does not have a specific position. So it does not have a specific position. One thing is very much clear. You already know, um, you already know that what does psi mod whole square represent. So I'll write it here. What does psi mod whole square represent? I'll write it here. So psi mod whole square represents probability density, right? Probability density. Let's say, okay, let us say I want to sketch a graph of psi mod whole square. So let us say I'll take the reference of Griffith, and let's say he says that, let's say this is how it is going to be. Let's say somehow this and this. Okay. So, and let's say this is my A and this is my B. Okay. So what does this area represent? This area under the graph, and let's say this is psi mod whole square and this is X. So this particular area which I'm shading right now, what does it represent? It represents the probability of finding the particle. It represents the probability of finding the particle between A and B. Okay, so psi mod whole square represents the probability density. And if I find area, what is area? You remember the area in integrals is given by this particular area would be given by integration a to b psi mod whole square dx. So this particular shaded thing that I'm writing is nothing but it is integration from a to b psi mod whole square dx. So it gives you what? It will give you the probability of finding the particle between A and B. Is that clear or not clear? This is one thing. Okay. Is that clear or not clear? Okay. Understand that there is a sense of indeterminacy in quantum mechanics with regards to the particle's position before the measurement has been executed. Okay. So I'll write it here. I mean, these are all sort of postulates only. Okay. So there is a sense of indeterminacy with regards to you can say, uh, with regards to uh, a particle's, let's say, position right now I'm stating before measurement. We don't know what is the before measurement. We don't know what it is. But once the measurement has been executed, we know what is the what you can say what is the fate, and that also we don't know with the full determination. That also we know with certain probability. So this is one of the fundamental, you can say, experimental outcome, you can say, one of the fundamental postulate on which your quantum mechanics is based. That is, prior to measurement we don't know what is the state. But once the measurement has been made, let's say right now we are making a measurement in the sense of determining the position. So before it, particle can be anywhere. Like on this particular graph, if I'm making, particle can be anywhere because the psi mod whole square represents the probability density. So you can say that uh, particle can be found anywhere. If I'm doing this particular integration, it represents the probability of finding the particle in this particular region. It does not negate me it does not negate me uh, an and a particular thing that I cannot find probability here. There is a certain probability of finding particle here as well. Okay, so let's say if I'm measuring some thing like let's say I'm trying to measure position. So with all determination, I cannot say where is my particle. I can say yes, the particle is here and there prior to measurement. But once I make a certain measurement, I would know that my particle resides here. I would know that my particle resides here. If this if I have to repeat that measurement, I will have to make it a very instant call, because after all this psi is a function of xyz, and it is going to it is going to evolve in space according to the time independent Schrodinger equation. So if I make it in a very rapid manner, only things can work, otherwise it may change the position. So understand, in quantum mechanics, one of the most important thing when we do is, in order to measure a particular thing, we make ensembles. We make what? Ensembles prepared in the same wave function, and we make repeated measurements. This is something called as taking an average value, or you can say expectation value. So this is an important concept in wave mechanics also, and the same we are going to see in matrix mechanics also. There I'm going to jot down all these points. But right now, since I have not formulated the definition of psi, it's a little bit difficult. But understand the point. Take it as a you can say postulate that there is an indeterminacy with regards to particles' position before measurement. I'm writing here in position. You can take this as well as momentum. And once you know momentum, then because p square upon 2m is what? Kinetic energy. So all these things will follow. All these things will follow. Is that clear or not clear? Okay. So I'll say that I'll write it here. So there is an indeterminacy with regards to particles' position before measurement, but after a measurement has been executed, measurement has been executed, there is a specific result. There is a specific result. But remember, this result also is probabilistic governed. This result is also probabilistic. Okay. Now, if a certain measurement has been made, let's say I make a certain measurement. Okay. I am very sure that my particle has been represented by a wave function, and let's say wave function is some way it is like this only. Let's say it is the way I'm making it. It is like this only. So same I'm going to trace. Okay, so let's say this is your okay. This is how it works. So let's say this is your A here, and let's say this is your B here, and let us say this is capital P, this is so and so, and let's say this is C, capital C, okay, and this is capital B, and this is psi mod whole square, and this is X. So after measurement, there would be some specific result. After measurement, there would be some specific result, but that is also not completely deterministic. That is also probability governed. I will say that a that particular measurement is gives you a result with a certain sense of probability, with a certain sense of probability. So what happens? Let's say when I do one of the measurement, and let's say my particle happens to be at C. So what will I see here? I will see a certain spike here. So if I make a measurement, and if I'm making a measurement of what? I'm making a measurement of position. Initially, I can say that particle is everywhere from here to here. Okay, I don't know where it is. Prior to measurement, I have no idea. But once the measurement has been made, let's say my particle is at C, so I'll see what? A spike over C. It represents what? It represents that my wave function, which was this, has collapsed to this particular thing. Has collapsed to this particular thing. So this is one of the experimental fact, and you can say this is one of the postulate. So if your particle is in general state, it is going to collapse into one of the eigenstate. So this is how it is said in wave matrix mechanics. But right now, when I have to show it in wave mechanics, it is a little bit difficult. Understand that the initially particle has been governed by psi, and psi is in turn governed by the a special evolution dictated by the time independent Schrodinger equation. So here your psi in general can be a function of time also, but right now I'm just keeping things simple. So it is a function of x, y, z, and let's say if it does not depend upon it is going to get evolved in space with respect to x and with respect to time as well, probably. So point is this particular equation governs the evolution of psi in the space. This particular equation governs the evolution of evolution of wave function in space. Now what happens is, once you make a measurement, there would be some specific result, and that particular specific result is also not completely you can say it's also not completely uh, you can say also does not have a particular sense of determinism. It is going to be probability driven. So I can say that yes, there is a certain sense of probability that a particle may be found at C. So once you make a measurement, and let's say it is at C, so there would be a spike. So what has happened? Your wave function has collapsed. So I'll write immediately after the measurement, the wave function collapses to a spike at C. And what does it say? It means that your particle is precisely at C. It implies what? That after measurement, you found that your particle is precisely at C. Okay, is that clear? Okay, so remember, this is one of the important postulate of quantum mechanics, which says that prior to the measurement, the in general, you cannot prior to the measurement, one cannot know what is a specific position of the particle. But after measurement, immediately after measurement, you know that there is a specificity, and that particular specificity is also driven by probability. Point number one. Point number two, now the question arises, if I make another immediate immediately after having known that the particle is at C, again if I make a measurement, what will happen? So I'm just writing it here. Now, another question that arises is, what if subsequent measurements are made? Let's say, what if subsequent, or let's say second measurement at first. Let's say first we are concentrating on the second measurement. So what if the second measurement has been made? So understand that what you can say, your Schrodinger equation. If I'm writing the complete Schrodinger equation, so what will happen? I will let's say I'm writing, this is my Schrodinger equation. Okay, let's say that it depends upon x, y, z, and let's say time also. So minus h ket square upon twice m, and then you have this del square psi upon del x square, and then you have this v and psi. So you know that this particular psi evolves in space as a function of x, y, z, and t, governed by this equation, right? It is governed by this equation, right? This is your Schrodinger equation, right? This is your Schrodinger equation in general. Is that clear or not clear? Okay. Now, if you're making a subsequent measurement, and if you're not making it too quickly, too quickly, your wave function will evolve in the space. It will evolve in the space as a function of x, y, z in time, governed by this equation. So if you are not making a second measurement quickly, then there would be change in the position. So at the very first place, you should understand, I've already talked that prior to measurement, you don't know the fate of the system. You don't know the fate of the system prior to the measurement. But let's say that I have already made a measurement and I've really found that it is at C. Okay, it is at C. Let's say first measurement I made, and the wave function collapsed to C. So what does it represent? It represents that once the measurement has been made, my wave function collapses to C. This is point number one. Now, the subsequent measurements, if I know that it is at C, then it will yield me C. Otherwise, I don't know about it. So what is the way? The way is to take something called as the average values. Is that clear or not clear? Please let me know. So how do we do it? Let's see, how do we take these average values? This is something that needs to be seen. So this is what I'm trying to explain now. So what happens is, I'm writing it here. Okay. So what I'm going to write it here, that let's say how to find this average value. And you understand why I'm saying it. See, again, understand, once I make a measurement, the wave function would collapse to a certain state. Let's say my particle was at C. So it is going to give me a spiky behavior at C. Okay. Now, if I am taking it very quickly, if I'm making another measurement very quickly, in a manner that it does not evolve in space. What does not evolve? Psi does not evolve in space. So I'm going to get back this C. Okay. So it is already very difficult that I assume that the particle does not change its position uh, in the subsequent measurement. In the subsequent measurement, it may have changed its position because psi also is governed by uh, a time sorry by Schrodinger equation. So psi evolves in the space as a function of x, y, z, that is the coordinates and time, according to this Schrodinger equation. So if it is not made very quickly, I cannot say that again the subsequent measurement would give me c. Okay, so the measurement theory in quantum mechanics uh, makes us uh, think about it, and we have to actually focus on something called as the expectation values or average values. Okay, expectation values and the average values. So how it is done? So I'm writing that. So in general, I'll say that. So in general, remember. So let's say there are n identical particles, and they are prepared in they are prepared in the same quantum mechanical state. Let's say psi of x. Right now I'm not taking it as a function of time. Right now I'm taking it as a function of x. Then a measurement of position of each particle. So if I try to take the measurement of position of each particle, it is going to give me, you can say, possibly different results. Okay, okay. So this is, you can say, this is experimentally governed. So you cannot do anything about it. Prior to measurement, you don't know. But once you make measurement, let's say in a system there are n different particles, even if they're if they are in the same quantum mechanical state psi x, I've told you that this psi x is represented by a sort of graph. Let's say if I say that, uh, let us say that it is governed by, let's say, Gaussian. So I don't know. So if all these particles, n particles, are governed by this particular, the wave function of all these particles are governed by this, let's say, Gaussian. After measurement, there would be different results. Okay, I cannot say that all of them are going to be in this region, all of them are going to be in this region. I don't know exactly. I only know that it may result in possibly different results, and this is something experimentally governed. I cannot do anything about it. So what is the way ahead? So the way ahead is to take the expectation values. So this is something that we are going to see later on, but we have to take expectation values or averaged values, and we'll see how to take this average. We'll see how to take this average. Okay, this is one of the important concept that I wanted to pay focus on. So I hope it is understandable. If there's something that you cannot understand, please let me know. Understand, this is something called as collapse of wave function. So prior to measurement, you don't know anything about precisely about your uh, position. Let's say right now I'm putting more focus on position only. uh, but after that measurement has been made, after measurement of what, let's say, accurately trying to determine, or you can say trying to determine what is the position of the particle, After the measurement, you will come to know that there is a certain spike. So your wave function collapses to a certain spike. So once it is collapsing to a certain spike, it implies what? Your wave function has collapsed to a particular state, and this is something called as eigenstate when we are going to see it in matrix mechanics, and also otherwise it is called as eigenstate. So one of the eigenstate. If a subsequent measurement has been made very quickly in a manner that psi has not evolved, only then you can argue that your wave function would again be at C. What I want to convey is if I make a subsequent measurement at a second measurement so quickly that your wave function has not evolved, only then I am in a position to state that I am at C. Okay. So in general, I know that psi is governed by your the Schrodinger equation, and I cannot argue this statement. So what I would do, the way is to make an ensemble prepared in the same wave function and try to do repeated measurements and try to take an average value. And this is sometimes referred to as expectation values. This is sometimes referred to as the expectation values. If it is clear, please let me know. We'll come to all these things, don't worry. But understand this fact is very important. That is why I'm focusing it on initially itself. Is that clear? Okay, good enough. Now, let us move to something called as normalization at first, and then again we'll come back to this same discussion, which is the discussion of expectation values. Okay, I hope I'm going very slow right now so that everybody is able to follow what I want to say. And these are very difficult topics. Uh, I don't know, but somehow these are very difficult topics to make people understand. But probably if I made a mistake here and there, please uh, excuse me for that. But precisely I want to explain one thing, that is why there is a need to take expectation value in general. Okay, this is something that I want to illustrate here. I'll come to this particular point later on, but let us first do something which is uh, more relevant to our business, which is normalization. Okay, see, I'm writing it here so that you are able to get. So see, understand one of the things is, see, understand that one of the things is that psi in general is a complex valued function. In general, it it holds no such physical interpretation. Rather, what is more physically interpretable, which is psi mod whole square. It represents your probability density. It represents your probability density. And if I multiply it with let's say d tau, I'll get the probability density. I'll get the probability of finding the particle between the volume tau to tau plus d tau. If I multiply it with let's say dx, I would get a probability of finding the particle in x to x plus dx. Okay, so in general, what is more important to us is psi model square, and it warrants us, or it actually is going to restrict us uh, to a certain class of functions which are called as L square. So we are going to discuss wave functions which are squarely integrable. Okay, and they form a certain vector space. They are going to form some Hilbert space, something that we're going to see later on. But I would say that we are only bound to see, we can only mathematically interpret a quantum mechanical you can say system in terms of wave function which is squarely integrable, which is squarely integrable. Okay, this is one thing. Now, having said all these things, why we need this particular squarely integrable function? Because after all, in order to find a particle somewhere in space, let's say if I say that my particle is in space, somewhere in the space, this probability should be 1. This probability should be finitely governed. There should be a answer. There should be an answer. If it's not integrable, then how things would work? How things would work? So our entire framework would collapse. So understand, we are only free to take only those functions which are squarely integrable in order to explain mathematically, uh, in order to explain mathematically. Let's say I told you, now the particle is represented in terms of wave function. So that particular wave function, we are going to only take those wave functions which are squarely integrable. Okay, this is something very necessary. Otherwise our this thing, our entire framework would collapse. Our entire framework would collapse. This is one thing. Now I'm going to write it so that it becomes easy for you. Okay, understand, since I know I know since we know that Schrodinger equation gives us a solution psi and it is linear. So it is, this equation is linear. Since this equation is linear, since Schrodinger equation is linear, so if psi is a solution, then a psi is also solution where a is some complex valued uh, constant. So let's say a is some complex valued constant, or you can say complex valued scalar. So if psi is a solution, then a psi also is a solution. Since Schrodinger equation is linear, so therefore I can say that if you can say if psi is a solution, then a psi is also solution. Okay. Now this particular a is referred to as normalization constant. So you can find this particular a, uh, since we know that our wave function is squarely integrable and probability of finding the particle somewhere in space is definite, that is unity. From that particular information, I can extract this a, and this a is at times referred to as a normalization constant. Okay, so how do I say, how do I say this? I will write it as that since psi, you can say psi is squarely integrable, since psi is square integrable, the normalization constant is chosen such that the normalization constant a is chosen such that integral minus infinite to plus infinite, you can say psi mod whole square dx right now is equal to 1. If it is, then from here you can extract the value of a. From here you can extract the value of a, and this a is called as the normalization constant. Okay, is that clear till now? Now you see, there are certain constraints. There are certain constraints, or you can say there are certain conditions which are required for psi, and these conditions, we say that for a physically realizable wave function, what are the conditions? So conditions for physically realizable wave function. And what are those conditions? Condition number 1 says that your psi x comma t should be finite, single valued, and continuous everywhere in the space. This is one thing. Okay. Second thing that we've already seen, that psi x comma t must be contained in the set of squarely integrable functions. That is, it must be squarely integrable. Another thing is that as x tends to plus minus infinity, as x tends to plus minus infinity, you can say that your psi x must go towards 0. Your psi x must go towards 0. Okay, and the fourth one is you cannot say anything about d psi by dx. It may be possible, may be continuous, or may not be. So we'll see that there are cases where it's d psi by dx is not continuous as well, may be continuous or discontinuous. This we'll see later on, but overall understand. Let's say if a particle is traveling somewhere in space and it encounters a Dirac delta potential, encounters a Dirac delta potential, then this d psi upon dx will bear discontinuity. So d psi upon dx will bear a discontinuity. So if your particle is, let's say, encounters an attractive Dirac delta potential, or let's say in general Dirac delta potential, then your d psi by dx will bear a discontinuity. This is one thing that I wanted to lay more stress on. Okay, so all these things are like something that we probably everybody has done till BSc section, so that is why I was just trying to revise all these things for you. One important thing that I want to stress, and then probably we'll end this lecture, which is that so let us say we have normalized our wave function. Let us say we have normalized our wave function at t equal to 0. So don't you think that as psi evolves in space and time, in space and time, will it remain normalized? Will it remain normalized? Okay. So let's say since A is evolving, if since psi is evolving, sorry, if A is also evolving in space and time, that is, if A is a function of time, then we'll have to normalize it at every instant, right? Will it not become very difficult for us? This is what I want to question. Okay, so one of the important properties of Schrodinger equation is that it preserves what you can say the normalization constant. So I'll write it here. One of the remarkable properties of Schrodinger equation okay, one of the remarkable property of Schrodinger equation is that it preserves the normalization constant or normalization of the wave function. That A is not going to evolve in time. Okay, It is not going to evolve in time or in space in general. So if you found a normalization constant, let's say at t equal to 0, then this a would remain forever. So it's not going to evolve. So it preserves the normalization of wave function. So this is one of the remarkable properties of your Schrodinger equation. Now another question that may arise is whether uh, Schrodinger equation confirms the conservation of probability also. By what by which what I would mean is that uh, what should I mean? Let's say if I'm saying that the Schrodinger equation preserves the normalization constant, uh, does it also preserve the probability? That is, what should I write as a question? I should write it here. Um, just give me a minute. Let me formulate what I want to say. Okay. So what I want to suggest was that if if I am saying that probability of finding a particle is unity somewhere in space, this probability must remain 1 irrespective of time, isn't it? So I would write it in a question form so that um, for consistency, for consistency, the total probability, the total probability of finding the particle somewhere in space must remain one, must remain unity at all times, isn't it? It should not be that, let's say I'm saying that okay, at this particular time t you have one, and for other times you don't have this. So there should be conservation of probability also. Okay, there should be conservation of probability. Okay, so this asserts, or this leads us to a question that whether, I'll write it here, whether the total probability of finding the particle somewhere in space is conserved or not. So let us see that, and this brings us to the end of the lecture. So I'll do this, and then we shall limit this lecture. There is a little bit more time I've taken. Okay, let it be. So let us try to prove it. So what do we want to see? We want to see the conservation of probability with respect to time. We want to see the conservation of probability with respect to time. And what does it mean? So if I'm saying that my probability of finding a particle in space remains conserved, that implies with respect to time, if I want to take the derivative of minus infinity to plus infinity, this particular derivative must be equal to 0. This is what we want to prove. And since we know that this x is a function of time and as well as space also, if I want to take the derivative, I can as well as write it as minus infinity to plus infinity. I can take a partial derivative inside, because inside I know that my psi is function of both x and t. So inside I cannot take the total derivative. I'll stick to the partial derivative with respect to time. I hope I'm making some sense. And all these things are given in Griffith and other good leading textbooks, but just understand why do they do all these things, okay? So now, having said all these things, I know that my psi mod whole square is what? Psi mod whole square is simply psi star into psi. And if I take a partial derivative of psi mod whole square, it is going to be psi star, and then you'll have d psi upon dt, and then plus d psi star upon d psi star dt, and then you will have this psi. And we already know that my Schrodinger equation, what is that? Iota h get del psi upon del t. So I have not derived this equation in general. See, the there's a book called as Arthur Beiser, which derives this particular equation using a de Broglie concept. I may do so, but I'm right now sticking onto uh, writing this particular equation because I believe everybody knows this equation. So I'm not pondering a lot amount of time into it, and my initial focus is to not uh, divulge into the philosophical connotation, philosophical interpretations that this may bring. My initial idea is to somehow put this equation into working and let you help with this thing. Otherwise, the measurement theory in general in quantum mechanics is quite an open subject even as of now. Okay. So right now, because since I don't want to get into all those technicalities, right now I just want to focus on this particular thing. So iota h get del psi upon del t, and it is equals to h get square upon twice m, and then you have this del square psi on del x square, and then you have this vxi. Okay, this is something that you know already. Okay, so if I want to write this del psi upon del t, from here also I can write my del psi upon del t is nothing but it is equals to uh, iota h get divided by twice m, and then you have del square upon del x square, and then you have minus iota upon h get b psi. And if I take a conjugate of it, so I'll get okay. So if I take a conjugate of it, I'll get this. So if I use these two here, what I'm going to get, so if I use both of these things here, what I'm going to get, so I'll write that del by del t of psi model square, which is equals to this particular fellow. And if I multiply all those things, so what I'm going to get, I'm going to get iota h get upon twice m, and then you have this psi star, okay, and this particular fellow will go off. See, if I add these two up, if I multiply psi star here and if I multiply psi here, this will get cancelled. Only I'm left with this. So I can write it as this way, that my del by del t of psi mod whole square is equals to del by del x of, I'll write iota h get upon twice m, and then you have this psi star del psi upon del x minus uh, what should I write, del psi star del x psi. If you do this, you are going to get a there is a term which will contain del psi upon del x and del psi star upon del x, which would get cancelled, and eventually you are going to get this only. You are going to get this only. The upper statement is equal to writing this statement. Okay. Now, if I take an integral, so I know that my d by dt of integration minus infinite to plus infinite psi mod whole square dx is equals to del by del t of psi mod whole square dx integration, and from minus infinite to plus infinite, and this is equivalent to this. So I'll write this is equivalent to writing So if I integrate this with respect to this particular fellow, if I want to integrate with respect to x, what am I left with? I'm left with iota h cat upon twice m from minus infinity to plus infinity. Okay. Now see, uh, in general, if I consider psi to be any squarely integrable function, then I may say that okay, it may be so possible that it may not vanish at infinity and plus minus at minus infinity. But my physics requires me that that psi x must vanish towards plus minus infinity. So if I take plus infinity, this particular thing would vanish, and if I take even minus infinity, this particular thing would vanish. So this will become zero. This will become zero. What does it imply? It implies that d by dt of minus infinite to plus infinite psi mod whole square dx is equals to 0, which implies what? It implies what? That my probability is conserved. Okay, and let's say at t equal to 0, if I found a normalization constant a, it will also remain constant. It will remain constant because you know that for finding a, what we do, for finding a, what we do, we actually use this particular statement that psi mod square deta integration is 1. So once if I have found a normalization constant a, having proved that probability remains conserved throughout and it does not change as a function of time, so a also does not change as a function of time. It implies that normalization constant also remains, like normalization once done at t equal to 0 remains constant throughout. Is that clear or not clear? So this brings me to the end of this particular lecture. We're going to meet tomorrow. Uh, a little bit of sketch I have already drawn. So probably tomorrow also I'm going to little bit digress more on this wave function part only, so that it becomes a little bit more clear to you. I hope you are liking these lectures. I'll meet you in the next lecture with a little bit of linear algebra, and we'll see things tomorrow later on.